Welcome everyone, and thanks for tuning in. I am Yang Liu, and I'm a research scientist at Abacus AI. Today, I'm going to talk about optimizers used in neural networks. The scope of today's talk is first-order optimization methods for artificial neural networks. I will first do a brief introduction to neural networks and how to train them with gradient descent. Then, I will talk about variants of two very popular optimizers, namely stochastic gradient descent and ADA. For people who are interested in more recent development, I will also introduce some new optimizers developed in the past few years. Finally, I will conclude the talk with some practical tips and a summary. Without further ado, let's dive into the first section. In the past few years, we saw an exponential growth of the power of deep learning. And deep learning is powered by neural networks. In 2015, a group of neural network models called ResNet officially beat humans in the ImageNet Large-Scale Visual Recognition Challenge. In 2017, AlphaGo, a neural network-powered Go player, beats world's #1 human player Ke Jie in the game of Go. And then in 2019, AlphaStar, a neural network-powered gamer, reached Grandmaster level in the popular multiplayer game StarCraft 2. At that time, it ranked top 0.2% among all human players online. And deep learning models are not only good at beating us humans, they are also good at helping us. Since the unfortunate onset of the pandemic last year, a lot of in-person meetings have moved online. The virtual background feature in many online meeting softwares is made available by a real-time video segmentation model that separates you from the background. And virtually all your smart voice assistants and your phone or your home speakers are powered by some kind of speech recognition network. By now, some of you might wonder, what is a neural network and how does it work? I'm pretty confident that many of you in the audience are veterans in deep learning and already know the answer. But please bear with me while I give a brief introduction to neural networks for those of you who are less familiar with the field. An artificial neural network is based on a collection of connected units or nodes called artificial neurons, which loosely model the neurons in a biological brain. The neurons are usually grouped into layers. And a neuron typically takes a weighted sum of the outputs of neurons in the previous layer, and then pass the signal through an activation function and then to neurons in the next layer. If one could properly set the weights of each neuron, the neural network as a whole can approximate almost any desired function. Okay, that sounds easy enough. Let's say we want to get a neural network model to tell us whether a picture contains a Okay, that sounds easy enough. Let's say we want to get a neural network model to tell us whether a picture contains a cat. And we're diligent enough to have collected a bunch of labeled images, and we have picked a neural network model. But now, how do we set the weights so that we can have a model that knows what's a cat and what's not a cat. It turns out a lot of practical problems, such as determining whether a cat is in an image, have no closed form solutions so that we could just directly solve for the weights. But what we can do is measuring how close our model's prediction is to the ground truth label and make small iterative corrections so that the model will gradually learn the desired weights. Formally, the most popular family of methods to optimize neural network parameters is gradient descent. You need a differentiable loss or error function to quantify the error between the output of your model and the ground truth label. And you also need an optimizer to update the weights accordingly. To give a concrete example, let's take a look at this single neuron model with n inputs and an activation function of phi. Formally, we could write the activation of this neuron J as this. It first computes the weighted sum of the network input J and then pass it through the activation function phi to produce the final activation OJ. We could then define a loss or error function E, which computes the difference between the output of the neuron and the target. With everything set up, we can compute the partial derivatives of the error with respect to a weight, let's say Wij. And mathematically, it is done using the chain rule twice. And in a real neural network with many layers, the gradient of a layer is computed from that of the next layer. Hence, the gradient is backpropagated from the last layer to the first layer in a network. Now that we have the gradient for the weight, what do we do with it? Because our goal is to minimize loss, the most intuitive way to do is to take a step against the gradient direction. This is called gradient descent. Formally, at step T, we update the weight by subtracting the product of the gradient and the step size alpha. In most practical applications, there are usually thousands to millions of weights in a model, and updates are computed with matrix operations in parallel for efficiency. Practical neural network optimization happens in a very high dimensional space, which makes it extremely difficult to visualize. Here, I give a visual example of gradient descent in action by considering a very simple toy loss function with only two inputs, x1 and x2, and the global minimum is at 0, 0. We could visualize the contour of the loss surface, and when we start at a random location in the 2D space, we could perform gradient descent with our simple 2D model, and in a few steps, we have reached the global minimum. And now you have seen simple gradient descent in action. In practice, it is very slow to compute the gradient based on all of the data points in a very large data set. A practical and more efficient alternative is to use a single data point or a mini batch of data points to estimate the gradient. And this is called stochastic gradient descent, SGD. Each individual gradient estimate will have some noise, but if we sample the data points randomly, and then the gradient estimate over many iterations would point to the true gradient direction. So SGD works in this very simple toy problem. And what if we make it a little harder? In this 2D optimization problem, the gradient in the x2 direction is much higher and changes much more rapidly than in the horizontal x1 direction. Here we have two undesirable options. First, we could pick a small learning rate and ensure that the solution does not diverge in the x2 direction. This way, the convergence in the x1 direction is going to be very slow. Alternatively, we can pick a large learning rate so that we move fast in the x1 direction, but then we diverge in the x2 direction. It seems that neither option is ideal. How can we fix it? Momentum is proposed to address exactly this problem by replacing the current gradient in the weight update with the exponential moving average of the current and past gradients. This would average out the oscillatory subcomponents of the gradients and help speeding up the convergence. If we think of optimization process as a ball moving downhill, the original SGD formula uses the current gradient directly to update the location of the ball. In contrast, momentum uses the current gradient to update the speed of the ball. In many cases, it would help avoid small bumps in the lost surface and then help converge faster. A fun fact here, many articles reference the momentum method to the publication by Qian in 1999. However, the classical momentum was actually proposed over half a century ago by Polyak in his paper titled Some Methods for Speeding Up the Convergence of Iteration Methods, which was published in 1964. But momentum is not always helpful. Let's look at this toy optimization problem in one dimension. Again, we can think of this process as a ball that moves downhill in a one-dimension space. As it moves, the ball picks up momentum and keeps accelerating. And this is actually the desirable behavior at the beginning when we take the first three steps, because it speeds up convergence. However, step 4 would overshoot the global minimum because of its past momentum. It would be great if the ball gets smarter by having a notion of where it's going so that it knows when to slow down. The Nesterov accelerated gradient, or NAG in short, was proposed to offer such foreknowledge of the optimization landscape. The key difference between the regular momentum and the Nesterov momentum is how we compute the gradient of the model. For NAG, the gradient term is not computed from the current location of the model in parameter space, but instead from a position that the model would have ended up if we used the previous momentum to update. This might sound a little convoluted, but don't worry. Let's take a look at the previous one-dimensional toy example again. Let's say after 3 steps, we end up here. Instead of computing the gradient here, we first take a fake update step 4a based on its past momentum, and we end up here. We then compute the model gradient at its location and then find the gradient for B, which points to the left. Finally, we combine the gradient for A and momentum for B, and then make the real update 4. As we can see here, the final update 4 is smaller than 4A because the model foresees the future gradient and uses it to correct its momentum. In one-dimensional optimization spaces like the one we've seen, nag can act as a brake to slow down the model. And in higher dimensional spaces, such as this 2D optimization space, nag can also help to steer the model in the right direction. With the original Polyak momentum, the gradient for x1 is computed here. But in contrast, with nag, the gradient for x1 is computed here at the green dot. The difference in where we compute the gradient results in nag updates landing the model in a location that is closer to the actual global optimum. Before we move on to adaptive learning rate optimizers, let's do a quick summary of what we have covered. I'd like to call the 3 optimizers SGD, momentum, and Nesterov accelerated gradient the SGD family. SGD itself is the most basic practical version of gradient descent. Both momentum and nag modifies how we estimate the gradient term to achieve faster and more robust convergence. In fact, all 3 of them are implemented in PyTorch under the optimizer class SGD, with momentum and nag being options. Despite their age, the SGD family is still the go-to optimizer for many deep learning models, especially in computer vision. Many of the state-of-the-art models in computer vision are still trained with momentum or nag with weight decay. The previous family of optimizers focused on making modifications to the gradient term, either to speed up convergence by adding momentum or offering some kind of foreknowledge to correct the gradient direction. But by default, the step size alpha is fixed for all parameters in the model. And this is less of a problem in smaller models. But in large and heterogeneous models, the optimal step size alpha could vary dramatically for different parameters. Before the advent of adaptive optimizers, people usually have to manually tune learning rates for individual parameters to get best results. If we could make the learning rate adaptive by automatically adjusting it based on some estimate of the typical size of the gradient of a parameter, we could save ourselves a lot of hassle of manually turning a million learning rate knobs. As you might have guessed, there is a line of research that focused just on that. In 2011, Ducci proposed a modification to the learning rate term by making it adaptive. They call it AdaGrad. The idea is that the learning rate of a parameter is divided by its typical learning rate averaged over many optimization steps. In more detail, the cumulative squared gradient V at step t is calculated by adding the squared current gradient to the running mean of the previous step. The step size for a parameter is divided by the square root of the running mean V plus a small epsilon for numerical stability. The square root is necessary because when we calculate the running average, we're using the square of the gradient, and then we need to take the square root to scale it back. The advantage of AdaGrad is that learning rate for each individual weight scales with its typical gradient size, as its name suggests. But a big problem with it is that the cumulative squared gradient V increases monotonically with the number of optimization steps, meaning that the learning rate vanishes after many optimization steps. To solve this vanishing learning rate problem, Hinton proposed RMSprop in 2012. With this method, cumulative squared gradient is replaced by an exponential running mean of the squared gradient. By doing this, V is allowed to go either up or down in scale. And the learning rate no longer vanishes after many optimization steps. Another fun fact, RMSprop was proposed in 2012 by Jeff Hinton in the lecture slides for his class Neural Networks for Machine Learning, and it wasn't even published in a peer-reviewed conference or journal. Okay, before we move on to the next optimizer, let's take a short look back at the two parallel lines of research that we have covered so far. With momentum and nag, we're actually estimating the first moment of the gradient. And on the other hand, with RMSprop, we're actually doing the exact same exponential average calculation, but with the second moment of the gradient. Now you might think, what if we combine both first and second moment estimate into one optimizer? And well, congratulations, you have just reinvented Adam, which arguably is the most popular optimizer for deep learning. As of yesterday, the Adam paper has accumulated more than 60,000 citations, and that averages more than 10,000 a year, and that's crazy. Okay, now let's take a closer look at how it's implemented in detail. Essentially, our intuition was correct to combine the first and second moment estimate in the update. And we have two betas to control how much we want to average these two moments, MT and VT. The only minor deviation from our intuition is how we handle the moments. In Adam, we use debiased versions of these moments instead of the raw ones. Debiasing is necessary because the running means are initialized to 0. And in the beginning of learning, there are not enough steps to average so that both moments would be biased towards 0. And when step count t is large, the denominator in the debiasing step will actually converge to 1, essentially turning off debiasing automatically. In the next section, I'm going to talk about 3 optimizers that addresses a variety of practical problems in deep learning. The first 2, LARS and SGD, are proposed to solve problems in large batch distributed training. And the third one, SAM, was developed to improve model generalization and reduce overfitting. A common way to speed up training for large convolutional neural networks is to add computational units. Training is then performed using data parallel synchronous SGD with mini-batch divided between computational units. With an increase in the number of nodes, the batch size also grows. But training with large batch size often results in lower model accuracy. Yu et al. Showed that the current recipe for large batch trainings is not general enough. And to overcome this optimization difficulties, they proposed a new learning algorithm based on layer-wise adaptive learning rate scaling, LARS. And the essence of LARS is per layer learning rate lambda. And the per layer learning rate is proportional to the ratio between the layer norm of the weight and the layer norm of the gradient. Using LARS, the authors scaled AlexNet up to a batch size of 8,000 and ResNet 50 up to a batch size of 32,000 without any loss in test accuracy. Another problem with training large neural networks lies in the requirement of distributing learning across multiple workers, where the cost of communicating gradients can be a significant bottleneck. Signed SGD was proposed to alleviate this problem by transmitting just the sign of each mini-batch stochastic gradient descent. And the authors proved that it can get the best of both worlds, namely compressed gradients and SGD level convergence rate. On the practical side, they showed that the momentum counterpart of signed SGD is able to match the accuracy and convergence speed of Atom on deep ImageNet models. They also extended their theory to the distributed setting, where the parameter server uses the majority vote to aggregate gradient signs from each worker and enabling 1-bit compression of worker-server communication in both directions. Finally, they proved that the majority vote can achieve the same reduction in variance as full precision distributed SGD. Thus, there is great promise for sign-based optimization schemes to achieve fast communication and fast convergence. SAM. In today's heavily over-parameterized models, the value of the training loss provides few guarantees on the model generalization ability. Indeed, optimizing only the training loss value, as is commonly done, can easily lead to suboptimal model quality. And motivated by the connection between geometry of the loss landscape and generalization, the authors introduced a procedure for simultaneously minimizing loss value and loss sharpness. Sharpness-Aware Minimization SAM seeks parameters that lie in neighborhoods having uniformly low loss. This formulation results in a min-max optimization problem on which gradient descent can be performed efficiently. The empirical results show that SAM improves model generalization across a variety of benchmark datasets and models, yielding new state-of-the-art performance for several models and datasets. Additionally, they found that SAM natively provides robustness to label noise on par with that provided by state-of-the-art procedures that specifically target learning with noisy labels. Okay, a quick summary before we finish the talk. So today we have briefly introduced how to train a neural network and then two popular families of optimizers, namely SGD and Atom. And then we introduced some recent development of optimizers. What we didn't talk about is that good optimization doesn't necessarily guarantee good generalization, as overfitting might happen. And in fact, it happens very often. So here are some practical tips when you practice your own machine learning or deep learning. When you face a deep learning problem, you might want to try Adam first. So when you get it to train, you can then check whether it overfits, and then if it does, you could either reduce the model size or apply some regularization techniques, such as weight decay or early stop, or just try the SAM optimizer. So I hope this talk has been helpful to you, and thank you again for tuning in, and I will take some questions next. All right. I think so far we have one question. That is from Milan. And the question is, why do we use chain rule twice? Here, if you look at how we formulate this layer, essentially you would have a... I think so far we have one question. Excuse me, I have echo here. From Milan, and the question... sorry about that, because I'm watching my own stream. Essentially, the reason why we have to use the chain rule twice is very simple. It's because we have two layers of functions. So first we have a summation of a weighted summation of the inputs, and then we have a activation function. That's all the reason. So in practice, this only computes the gradient. This two chain rule thing only computes the gradients for a specific layer of a neural network. In practice, if you have many layers, you apply the chain rule many times. All right, guys, seems like you only had one question today, and thanks again for tuning in, and sorry about the technical issues, and hope you guys have a good day.